Hi everyone, welcome to our presentation on simulating transmon qubits using Python. So today I'll be explore the fundamentals of transmon qubits, their mathematical modeling and how to simulate their behavior computation. So, so this is the first overview of what transmon qubits actually are. So as we know, the transmon qubits are a type of superconducting qubit designed to reduce sensitivity to charge and noise, so thereby enhancing coherence times. So they are fundamental components in quantum computing, enabling the development of scalable quantum processors. So in this presentation, I'll delve into the simulation of transmon qubits, focusing on their mathematical modeling, energy spectrum analysis, and the impact of noise on their behavior. So now, what is a transmon qubit? So, in simple language, a transmon qubit basically consists of a Josephson junction shunted by a large capacitance, which forms a nonlinear LC circuit. So, this design minimizes charge noise sensitivity, making transmons more stable and reliable for quantum computations. So, transmon qubits are widely utilized in quantum computers for their scalability and improved coherence properties. So here's a mathematical modeling of transmon qubits, which is the behavior of the transmon qubit is described by this. We can describe by this Hamiltonian, which is h, which is equals to 4 times e c n cap minus n g squared minus e j cosine phi, where ec is the charging energy, ej is the Josephson energy, n cap is the number operator representing the number of the Cooper's pairs, Ng is the offset charge, and phi cap is the phase difference across the Josephson junction. So this Hamiltonian captures the energy contributions from both the charging energy and the Josephson junction, so providing a comprehensive model of the transmon qubits dynamics. So our primary goal in this simulation are to model the behavior of transmon qubits and analyze their energy spectra, and to understand the impact of noise on transmon qubits and their coherence properties. So we will utilize Python libraries with such as NumPy and Matplotlib for numerical computations and visualization, so implementing simulations to study the dynamics and stability of transmon qubits under various kind of conditions. So this is the way we have defined the transmon Hamiltonian in Python. So to simulate the transmon qubit, we first define its Hamiltonian in Python. So we will use the NumPy to construct the Hamiltonian matrix based on the theoretical model. And here is a Python function defined as the transaction Hamiltonian. As you can see, we have imported NumPy from the NumPy library as NP, and we have defined various other things in the code implementation. So in this function, so num level specifies the number of the charge states considered. EC and EJ are the charging and Josephson energies respectively, and N represents the charge states. So H is the Hamiltonian matrix with diagonal elements representing charging energy and off diagonal elements representing Josephson tunneling. So next we can see that about how we can compute the energy levels. So with the Hamiltonian defined, we can compute its eigenvalues and eigenvectors to determine the energy levels and corresponding quantum states of the transmon qubit. So here's a Python function to compute the energy levels. So as we can see, this function uses NumPy's lineage.aigh to perform eigenvalue decomposition, returning the energy levels, eigenvalues, which are basically the eigenvalues, and their associated quantum states, which are correspondingly the eigenvectors. So now we can head towards this visualizing the energy spectrum. So to gain insights into the transmon qubit's behavior, we visualize its energy spectrum by plotting the computed computed energy levels. So as you can see in the code implementation, we have shown the Python code that is required, the Python function to plot the energy spectrum. So this function uses matplotlib to create a scatter plot of the energy levels, providing a clear visual representation of the transmon qubit's energy spectrum. So our next slide is simulating noise in the transmon Hamiltonian. So in real world scenarios, the transmon qubits are subject to like environmental noise, which can affect their performance. So to simulate this, we introduce random perturbations to the Hamiltonian matrix. Here is Python function to add noise to the Hamiltonian. So as you can see, with the code implementation that the Python function we have used, and this function adds a symmetric random noise to the Hamiltonian, ensuring it remains Hermitian, which is essential for representing a physical quantum system accurately. So in the final slide, we can analyze the impact of the noise on the energy levels. So to access the impact of noise, we compare the energy levels of the original and noisy Hamiltonians. So here we have how we have done it. So this is the function. Here is how we can do this in Python. So this code actually computes and plots the energy levels of both the original and noisy Hamiltonians, allowing us to visually compare and analyze the effects of noise in the transmon qubit's energy spectrum. So so as you can see, this is our result, which is the energy spectrum of the transmon Hamiltonian, the energy spectrum of the transmon system, and consequently for the case of noisy as well. So if we just try to kind of briefly conclude what we have done and what can be the future scope from this work, which is going maybe some we can look for, which is in this presentation. So we have explored the simulation of transmon qubits, and the things that we have covered is we have explored the various properties such as like defining the transmon Hamiltonian, computing and visualizing the energy spectra, and then we sort of tried to assessing the impact of environmental noise on energy levels. So some of the key insights that we can draw from this presentation is transmon qubits exhibit anharmonic energy spectra, which are kind of essential to distinguish qubit states, and environmental noise introduces perturbations of energy levels, potentially affecting the qubit coherence and performance. So this is what we have tried to do and tried to achieve. So this was our presentation and kind of the rough video that we thought would be helpful for this project. So again, once again, thank you for listening to this video, and once again, thank you so much.